Thank you very much. I should like to say that it's a very great honor to be asked to give one of these popular lectures. It's also a considerable responsibility, but I've chosen a subject which I very, very much love. It's a subject, the mathematical theory of knots, in which I will be able to show you, I will be able to put to you some of the open research questions. Now, this is quite unusual in mathematics. It's more commonly the case that it takes a long period of apprenticeship, at least a first degree, and then sometimes more than that, before a student even begins to see some of the open questions, some of the research questions in the subject. There are parts of mathematics where you can get to those research questions more rapidly, and knot theory is one of them. It's also a subject with some very, very beautiful ideas in it, as of course many mathematical subjects have. And it's a subject in which we're dealing with very familiar objects, everyday objects. So I'm going to try and describe some of these ideas to you. One thing that you'll all be very familiar with is that when you plug your computer in to charge it up, and then it's charged up, and then you switch it off and unplug it, and you put the cables neatly away in your bag, and you go somewhere, and then you open your bag, and you take the cable out. It's all tangled up, isn't it? I'm not going to be able to help you with that at all. Okay. Now, so here we have a knot. Actually, it's a picture of a knot. Okay, let me try and show you what a knot is from my point of view. I can tie what you would normally call a knot in it, but it's not a knot yet. This is what you would normally use the word knot for. You could do something more complicated, but it's only when, for a mathematician, it's only when you join the ends of the string together to make a loop that this is now what a mathematician means by a knot. Okay? It's something that intrinsically it's just a loop. Intrinsically it's just a circle. But it's been put into our three-dimensional space here in a knotted way. In order to change the knot, I have to cut the string, which I can do with this one just by unclicking. And then I can do some more tangled things. This is a relatively simple operation that I'm performing now, of course. And then make it back into a loop. And I've now got a different knot, a more complicated one. So the idea of a knot is that you take a loop, you take a circle, actually, but not a circle that's a geometrical circle. You take a loop, and you put it in, so here's the loop, and you put it in space in a knotted way. So in order for us physically to do that, you have to cut the loop, tie what we normally think of as a knot, and then join the loop. Now, if I make a knot, I'll make a nice simple one like that. And now I can perform all sorts of, I can move it around, sorry. I can move it around, and I can even, this stuff is elastic, I can even stretch the elastic. And I think you'll agree that I haven't really changed the knot. I haven't changed the actual structure of that knot as a knot. I might change its position in space, I might rotate it around, I might twist it around in all sorts of different ways. But as a knot, it hasn't changed. And so what we've got is, you might think, how are we going to describe these things mathematically? And so what I've got is a curve in space here, and so you might think, well, why don't we just write down some equations for that curve? Well, that would be, for one thing, that would be a very difficult thing to do. The equations would be very complicated. But for another thing, it's not really the particular position of this string that you're interested in, and that's what those equations would tell you after all, but that's not really what you're interested in. You're interested in the knottedness somehow. And I want to try and show you how that knottedness can be captured and explored mathematically. That's what I'm going to try and do with you. That's a picture of a knot. Now, I think you'll agree that the same knot could have lots of different pictures. To get a picture like that, what you would do is you'd make your knot, and then you'd project it. You could put it on an overhead projector and project it, and you'd get something looking like that. Okay, but that same knot, you could move around and put it down on the overhead projector in a different way. You haven't changed the knot, but you'd certainly get a very different picture. So you're going to get lots of different pictures all for the same knot. Now, some of you might have wondered a little bit about this particular picture. Let me show you something. You might have guessed. You might have guessed. I don't know why it speeds up at the end. It's not me. Let's do that again. So that's the starting position. Watch carefully. Okay, so I'll do it again. There's the starting position. So that original thing that looked like a knot when you just sort of looked at it actually wasn't. It was just the straight loop. It was what we call the unknot or the trivial knot. It wasn't knotted at all. It's just that it had been scrumpled up a bit. And so that's a warning to us that we're going to have to be very careful if we're going to use pictures of knots, which we are. We're going to have to be very careful to make sure that we don't get fooled. That we're dealing with the unknot, perhaps. Let's now look at some more pictures, some diagrams of knots this time. Those numbers are pretty small, but I can show you what they are. Just to the left of each of the diagrams, there's a number. Actually, it's two numbers. So the top left up there is 3 with a little 1 hanging off it. And then below it, it's 4 with a little 1. And then below that, it's 5 with a little 1. And the 3 is the number of crossings in the diagram. Okay? And then below it, there are 4 crossings in that second knot down. And below it, there are 5. And now there are 2 knots there with 5 crossings. And so they're just labeled the 5 crossing knot number 1 and the 5 crossing knot number 2. So that's what 5-1 and 5-2 means. And then you get a 6 crossing knot, another 6 crossing knot, and another 6 crossing knot. And then you've got a whole column of 7s, and then you've got 3 columns of 8s. Okay, so down here, this is the 21st 8 crossing knot. The order in each category is arbitrary. Okay, just a convention. But you can see that each category is quite distinct. Or can you? I mean, even that is a question we have to think about for a minute. I could take that very first knot, which was the one I made, and I could make a more complicated diagram of it just by doing some more things to it, but without changing the knot. I'm not cutting it, I'm just twisting it around. And I get a very much more complicated diagram with many more crossings. So what do I mean when I say that first knot up there is the knot with 3? What I mean is that is the simplest diagram of that knot. It's the diagram with the smallest number of crossings. And if given a knot, you play around with it until you can find somehow the diagram with the smallest number of crossings for that knot, then that's what's called the crossing number of that knot. And so that very first knot, which is also known as the trefoil, is a knot which has a diagram with 3 crossings. And in fact, it's the only knot which has a diagram with 3 crossings. And then next down, there's a knot which has a diagram with 4 crossings, but no diagram with 3 crossings. And that's 4-1. And then you've got a knot 5-1, which has a diagram with 5 crossings, but no simpler diagram. You can make any of those knots, and you could make them arbitrarily more. You could make the diagrams arbitrarily more complicated, but that would be a silly thing to do. There are many more knots than this. And this is a good start. We're going to learn a little bit more about some of these. This now is a slide showing you how. So this is very good news. This is a wonderful theorem by Reidemeister, who proved it in the 20s. If you've got 2 diagrams, right? Suppose I draw 2 diagrams. How do you know? It's possible that they represent the same knot, but they just sort of they're just different diagrams of the same knot. How would you know that they were diagrams of the same knot? Well, Reidemeister proved that if you can get from one diagram to the other diagram by just using these 3 moves, then certainly they're diagrams of the same knot. And conversely, even more importantly, if they are diagrams of the same knot, then you only need these three moves, a combination of these three moves, to get from one diagram to the other one. So in other words, I mean, if you've got a diagram which has just a, I mean, you've got lots more diagram down here, imagine, and you've just got a simple, silly bit on it like that, then it's clear that you can just do that, okay? It's very clear that doing that doesn't change the knottedness. And that's Reidemeister 1. Reidemeister 2 is when you have two bits of the same diagram and you just put them, they happen to fall on one on top of the other. And that's not changing the intrinsic structure of the knot to do that. And Reidemeister 3 is when you've got a crossing somewhere in your diagram and you move another piece of knot over it. So these are simple operations on the diagrams. And the key point of this theorem is that those are the only operations that you will ever need. So if two diagrams do represent the same knot, then you will be able to get from one of those diagrams to the other one by combinations of those moves. So that's the good news. It means that we've got a chance now of, instead of trying to understand how to describe these knots, I mean, actually they're things in space, but we're now going to consider drawings of them, and we have, in principle, a way of telling when two drawings represent the same knot. So that's the good news. The bad news is that, well, there are two bits of bad news, actually. One is that if I've got two diagrams, and I'm pretty sure they're diagrams of the same knot, I've got reasons for believing that, so I'm looking for a sequence of Reidemeister moves that take me from one diagram to the other one. I might have to make the picture much more complicated. In other words, I start with a diagram here, suppose it has 15 crossings. I might have to put more crossings in before I start to simplify again and get down to the other diagram. And that makes the complexity of the problem is very hard. It makes it very difficult to actually encode this problem. There's no upper bound on the complexity of the intermediate steps that you might have to take in getting from one diagram to the other. So that's a piece of bad news. Another piece of bad news is this. Suppose the two diagrams are not diagrams of the same knot. Then the Reidemeister moves don't help you at all, actually, because to show that they're not representing the same knot, you can't show that there's no sequence of Reidemeister moves, because you can't look at all possible sequences of Reidemeister moves on one of the diagrams and not get to the other diagram. So that's the other piece. So although this theorem is an extremely important one, it does lead us to some really deep questions. Okay, but let's leave that aside for a minute. Let's now turn to ask the question, how many knots are there? Well, so here's an extraordinary table that Thistlethwaite and co-workers produced some years ago, which was also featured in the Mathematical Intelligencer, actually. Tonight's guest publication. So we saw in that previous table of knot diagrams just now that there was just one knot with 3 crossings in its smallest diagram. There's one knot with 4 crossings in its smallest diagram. There are 2 with 5, 3 with 6, 7 with 7, and 21 with 8 crossings. And that was as far as that slide went. So what after that? Well, there are 49 with 9 crossings, and so on. 165 with 10 crossings, and 1,388,710 with 16 crossings. And that's as much as is known. People are working on the 17 crossing problem, and it's difficult, okay, as you can imagine. How on earth do you begin to get these extraordinary numbers out? Well, of course, you use a computer, and of course, just as we saw earlier, you can't just switch one on and tell it to calculate. You have to be very, very clever in how you make the machine work for you. And the first thing you face is, how are you going to encode in a computer a knot? And I'm going to explain what a prime knot is. A little bit like a prime number in that it's not a composite. So what's a composite knot? Well, here's a composite knot. If you take 2 knots and put them next to each other and then join them in that way, then you get a composite, okay? So the knot that you would get by joining like that is not prime. So that tells you what prime knots are. Let me now tell you how you might, there are different ways of doing it, but Thistlethwaite and his colleagues used this code, I think it's called the Dowker code, for a knot diagram. So you've got a diagram of a knot here. What we're going to end up with is a sequence of integers that describes that. You place a spot somewhere on the diagram, which is that black spot up there, and you start walking along the knot. And I want you to walk upwards towards where that number 6 is. But the number 6 isn't there yet, okay? Imagine that it's not there. What we're going to do is we're going to walk around the whole thing. Notice that when we do that and get back to the black spot, we're going to visit each crossing twice, of course, because it's a crossing, okay? So if you walk around the whole thing, you're going to visit each crossing position twice, once under and once over. When you walk up to that first crossing, call it crossing number 1. Remember that, call it crossing number 1. Then keep walking along to the next crossing, which has got a 7 there, which you can't see. Call that crossing number 2. And then keep walking, come down here to this crossing here. That's crossing number 3. And can you see what's happening? Crossing number 1 has a 6 associated with it. 2 has a 7 associated with it. 3 has a 10 associated. We'll come to those other numbers in a minute. Where were we? We're 3. Come around to here is 4. Go up to there is 5. Come around to there. Now we've got 6. We've visited that first crossing twice now. The first time we labelled it 1. The second time we labelled it 6. That's why that number 1 is paired with that 6. And you keep going until you've got that pairing. And you'll discover when you think about this for a minute or two that actually what happens is that the even integers get paired with the odd integers. So the code for the... and we already know there's a sort of an obvious, a standard order for the odd integers. You put them in standard ascending order, and then you throw them away. And the code for this knot is then 6, 10, 8, 2, 4. So you can put that, you could actually now program a machine to generate lots of strings of digits like this, okay? And more importantly, of course, you can reverse this procedure. Given a string of digits like this, you can actually construct the knot diagram. So now you could imagine generating lots of strings of digits, and that generates for you lots of knot diagrams. But that's only just the very beginning. You've got to be much, much cleverer than that before you get that table of knots at Thistlethwaite. You see, one of the things that you want to avoid is a knot diagram where you've just got a silly extra loop, which you could remove by using Reidemeister 1. So the diagram has just a silly extra bit on it that you can just undo, okay? How would you recognize that in these strings of digits? Well, if you think about it, if you just had a diagram where you go up here and then cross over yourself and then back into the diagram, what that would do is that crossing gets visited twice immediately. So whatever number you gave it when you first visited it, you get the next number as you come back to it again. So if you see any code which pairs a number with an adjacent integer, then that tells you straight away that that code represents a knot diagram with a silly Reidemeister 1 curl in it, which you can get rid of. So that's just the beginning. That tells you that when you generate these strings of digits that are representing knots, you then want to put these strings of digits through various sieves that throw out all the silliness like that. And this team of researchers were very, very clever in designing successive sieving procedures that, having generated all these diagrams, just removed all the dross and left you with the actual list of prime knots. Here's another way of representing knots in a way that could easily be encoded digitally. This, I believe, is a much older method. I've only just come across this recently. I'm very ignorant about these things. So we're going to end up with a knot in a minute. You start with some grid like that, and you have a rule that you put a naught and a cross so that each row and each column has a naught in it and a cross in it. Okay? And I think you'll agree that that's one such pattern. So you just choose a grid of any size. You can easily do this. You just choose a grid. You choose it as many rows and columns as you like. But the rule is that each row and each column has to have both a naught and a cross in it. And then you do this. You join the naught to the cross vertically in each column. Then you join the naught to the cross horizontally in each row. And the rule is you always go under the vertical lines that you've already drawn. And now you've got something which isn't a knot. It's a link. What's the difference? Well, a link is when you start with more than one loop. Okay? I mean, I started just now with just one loop, but I could have started with more than one. And actually, the theory of knots, sometimes people call it the theory of knots and links, or the theory of links, and sometimes people aren't so careful about the words. In general, you could start with any number of loops and ask how they can be put into space. So you take a loop, you tangle it up somehow, and while you're tangling it in with another loop as well. And then I'll move to the other loop and do a bit of work on that. I'm just going to end up with a mess. I'm not doing anything clever here. And now I've got something which, if you couldn't see these black bits, I mean, these black bits tell you how many components this link's got. It's got 2. But if they weren't there, if it was all continuous red stuff, then you wouldn't know, obviously, it wouldn't be completely obvious how many components this thing had. It would just look like a knot. Actually, it's a link. It's got 2 components. So this procedure, you can easily play with this. You can encode that information digitally, and that information contains the link in this case. I did promise you at the beginning that I was going to give you some hard questions. So here are some. And this is the very first thing that I described to you, right? I was talking about crossing numbers. So the idea is you have a knot, which is actually a thing in 3 dimensions, but that's too complicated to cope with. And so you project it and you look at a diagram of it, and then you have to face the problem that a given knot has lots of different diagrams associated with it. And so you say, well, the intelligent thing to do is to choose the simplest diagram, if I can find it, which may not be easy. Choose the simplest diagram, which represents that knot, and then count the number of crossings in that diagram, and that's called the crossing number of the knot. Now, that hash symbol there is the joining of 2 knots. You remember when I just said what a prime knot was, I described that by saying what it wasn't. Okay? So I said if you take 2 knots and you join them together, that's what that. So K hash L means take knot K and knot L and join them in the way that I showed a few slides ago. And you might think, and this is an absolutely open question, is it true that the crossing number of a join of 2 knots is the sum of the crossing numbers? Well, it is true in a certain special case. It's true if the joined knot is alternating. So I have to tell you what alternating means next. I'll come back to this picture in a moment. Let's look at our table of knot diagrams again. Almost all of these are alternating, not quite all of them. Alternating means that as you walk around the diagram, you alternate between going under and over, under and over. And if you look at some of these, you'll see that. So I mean, here I'm going under, over, under, over, under, over, and so on. As you walk around, you alternate. Now, it's rather misleading, because actually, if you just play with this table, it would take you a while to spot that not all knots are alternating. This one here, I think, is the first one which isn't. You can see there are 2 overcrossings. As you walk up that vertical bit there are 2 overcrossings adjacent to each other. That's 8 sub 19. That's the 19th knot in the 8 crossing series, and that's not alternating. This is not alternating. This is not alternating. So, and then you go further and you discover that actually alternating knots are rather rare in the universe of knots. They're very common down at the baby end, which is where we are, where we're looking at the very simple knots, but they're rarer as you get further out into the knot zoo. So let's go back to that question. Is it true that the crossing number of a join of 2 knots is the sum of the crossing numbers of the 2 knots? That would be nice if it were true. It's a nice equation to have. It is true if the knots are alternating, but that doesn't get you very far, because as you get further out into those millions of 16 crossing knots, alternating is rather rare. So that's an open question. If any of you solve that, publish it. Okay. Now another question is to do with another number that you can associate with a knot called the unknotting number. So if I make a knot, I will keep it simple, actually. I will keep it simple, but not as not. Now, so the question is, so this is my 3 crossing knot. Okay, it's got 3 crossings. It's the trefoil. It's the one at the top. It's the one at the top left of that picture we had. And the unknotting number. Suppose I'm allowed to cheat. Suppose I allow myself to cheat, and I can cheat with this particular device. Suppose I allow myself very carefully to break the string at a crossing, change the crossing, and make the string up again. What happens? I get the unknot. Okay. So what happened there was I had a crossing which was a particular way round, and I deliberately changed just that crossing, which is illegal, okay, for knot theory. But what I'm going to do is I'm going to say, if I allow myself to make a crossing change at a specific crossing, would that be enough to unknot the original knot? And in general, it isn't enough to just change one crossing. It might need more than one such change. So given an arbitrary knot, a diagram of a knot, how many crossing changes would you have to make? What's the smallest number of crossing changes that you'd have to make in order to unknot it? And that's called the unknotting number of the knot. And this is one of the 8 crossing knots. I think 1, 2, 3, 4, 5, 6, 7, 8. It's one of the 8 crossing knots. I think it's 8, 10, this one. And amazingly, the unknotting number of this was not known. It was an open research question until 3 years ago, 4 years ago, a small number of years ago, 3 years ago, I think. And then Oshvath and Szabo, using some of the most sophisticated tools from algebraic topology, which is one of the hottest parts of mathematics. They were using tools right at the edge of the subject. They managed to show that the unknotting number of this thing is 2. Now you might think, that's completely ridiculous. Surely all you have to do is try it. You've got a diagram here. Surely you've only got 8 crossings. It's a very small, finite problem just to experiment with changing the crossings and to see whether one crossing change will unknot it or whether 2. I mean, it's known that there are 2 which will do it. The question is there just one that might do it? And surely you think, well, I can just test each crossing. So what were these people wasting all the... Well, it's much more subtle than that. This diagram is the diagram of that knot with the smallest number of crossings in it. Okay? It's not necessarily the diagram which exhibits the smallest unknotting number, which is very weird. There's another example, there's a 10 crossing knot, 10, 8, which is known to have just one diagram in which it exhibits its minimum number of crossings. And in that diagram, you can check in a very sort of simple algorithmic way that you only need 3 crossing changes, and you can unknot it. But if you choose to stay with that same knot, but choose a more complicated diagram of that knot, more complicated meaning it's got more crossings, it has a 14 crossing diagram, so you put 4 extra crossings in, but that diagram is not one that you'd normally play with, but it turns out that if you put more crossings in, then it only needs 2 crossing changes to unknot it. In other words, the diagram that minimizes the crossing number is not necessarily the same as the diagram which minimizes the unknotting number. And that's why that previous question, whether this has unknotting number, this knot, not this diagram, but this knot has unknotting number 1 or 2, was such a hard question. It's extraordinary that with relatively simple everyday things like this, we're testing the most advanced bits of algebraic topology that we can lay our hands on. It's one of the reasons that knot theory is so important in mathematics is that it's probing our understanding of topology and in particular our use of algebraic techniques in topology. Now what I'm going to do is return to an earlier problem, which I mentioned. Remember we had the Reidemeister moves, and I was saying if you've got two diagrams and you want to check whether they're diagrams of the same knot, then if you're lucky, you can find a sequence of Reidemeister moves which move you from one of those diagrams to the other one. And then I said, if on the other hand, the two diagrams represent different knots, then you have to do something else. And what you can do is find what we call an invariant. Find a property that would have to be different, right? That would demonstrate that those two diagrams could not possibly represent the same knot because they have different properties. Now, the particular invariant that I'm going to show you is an extremely famous one. It was discovered in 1985 by Vaughan Jones in a brilliant piece of a combination of very, very brilliant mathematical skill and taking advantage of a piece of luck. He spotted something in another branch of mathematics that he was able to use and bring into knot theory. And what we're going to do is we're going to associate with a knot a polynomial. Now, you all know about polynomials. They're these things that you play with. They're these sort of quadratic and cubic things, okay? You probably would never imagine associating a polynomial with one of these knotty things, but that's what I'm going to do. And it's going to be, so it's called the Jones polynomial, and we're going to build it up in a what's called a recursive way. It's a little bit like using mathematical induction. We build up from simple knots and show how to calculate this polynomial for any knot. So for our first axiom for this is, so P is the polynomial, okay? And P of the, and what we're going to do is we're going to have a polynomial P, and then in the brackets, I'm going to have a symbol representing a knot. Now, if I start just with the unknot, then the polynomial that I'm going to associate with the unknot is just the number 1, which is a very simple polynomial. Now, my next axiom says I'm going to relate. So what I'm going to imagine is that I've got 3 diagrams, okay? And these 3 diagrams are absolutely identical to each other, except in the neighborhood of just one crossing in each diagram. So you take a diagram of a knot, you decide you're interested in a particular crossing, and you make a photocopy of that diagram again and again. And around that crossing, you've got different things you can do. You can leave the crossing alone if it was that one. You can switch it, or you can undo it. You'll notice, by the way, that I've got arrows on those arcs. What I should have said was that this polynomial is for oriented diagrams. In other words, what you've got to do with your diagram is decide which way round you're walking. So you put an arrow. Imagine that there's something flowing along the electricity flowing along the knot in a particular direction. So you've got these 3 diagrams. They're absolutely identical, except in the neighborhood of one crossing where you've got these 3 possibilities. Now, each of these diagrams will have a polynomial associated with it, we imagine. I haven't showed you how to calculate that yet, but this is how it works. The 3 polynomials, there's the polynomial for that diagram which has that crossing in the middle of it. Here's the polynomial for that one, and here's the polynomial for that one. And these 3 polynomials are related to each other by this equation called the Skene relation. So x to the minus 1 times that polynomial minus x times that one plus this mess times that one equals 0. In other words, those 3 polynomials are not independent of each other, they're related. And that means if I knew somehow what this polynomial was, and if I knew somehow what this polynomial was, then I could use this equation, by fiddling about and doing some algebra, to tell me what that polynomial was. Now, how might that work? Well, the thing is that if I start with a diagram and I change one of the crossings, if I do it cleverly, I'll end up with a simpler diagram. And certainly, if I remove the crossing, I'm going to have a simpler diagram because I'll have one fewer crossings. So I start with a diagram and I choose a crossing, and I choose it in such a way that when I change it, the diagram simplifies. And then I hope that by iterating that procedure, I'll be able to use this relation again and again to, I'll show you. Let's actually do an example. So we're going to calculate the Jones polynomial of the trefoil. And in fact, the one that I'm going to calculate is the one in the middle. That's the trefoil knot. I'm going to call it T with a subscript minus, because the particular crossing that I want to look at, the one where the arrow is actually the negative crossing. And so what I'm going to do, so I'm going to calculate the Jones polynomial of that thing. It'll take 5 or 10 minutes, then I'll stop. And then, so what I'm going to do is I look at that crossing and I change it to the positive crossing. You see that they're identical diagrams except that crossing got changed. Or I smooth it, I undo it, which gives me T0. Now those two are simpler than the middle one. And in fact, the one on the left, I think you can see just by doing a couple of Reidemysters, the one on the left is not a knot at all. Okay? It's the unknot. So I know what the Jones polynomial of that one is. It's the number 1. So if I could work out what the Jones polynomial of T0 was, then I could put those two into my equation and work out, by doing some algebra, what the Jones polynomial of the trefoil was. So that's the Jones polynomial of T plus is 1. T0 is a link. It's got 2 components. It's got 2 pieces. The Jones polynomial actually works for links. We've now got to work out what the Jones polynomial is of that simplest possible link, actually simplest possible 2-component link. Okay, let's do that. Now I'm going to label that T0, I'm going to label it as, it's L minus. Look carefully at L minus, and now I'll jump back and I'll show you T0. And it's the same thing. Look at T0 and then jump to L minus. I've called it L minus because I want to look at that crossing in the bottom left there. And that's the crossing that I'm going to focus on next in my relation. So I change it, and I get L plus, and I smooth it, and I get L naught. Now, L plus, now, the 2 components of the link have now become separate, split. Okay? That L plus is just two loops, just completely unrelated to each other. I could move them miles apart. Okay? So there's a decent chance that I can work out what the Jones polynomial of that is. And L naught is just the unknot again. So I know what the Jones polynomial of that is. It's the number 1. Now, L plus is the disjoint union of 2 unknots. Now, you might think, OK, well, the Jones polynomial of that is surely 1 times 1. And it would be nice if it, well, actually, it wouldn't, Jones polynomial wouldn't be any good if that were true, in fact. It's just not, that's a reasonable first thing to think, that the Jones polynomial of 2 loopy bits unconnected to each other is just 1 times 1, but it isn't, okay? You can prove, it doesn't take very long to show that if you take any link whatsoever, so you imagine some horrible mess here, and you take a simple unknot out here and you move it in close and you ask for the Jones polynomial of the whole thing, it is the Jones polynomial of the link that you started with multiplied not by 1, but by this mess. Right? And therefore, the Jones polynomial of L plus is actually this mess. So it's slightly surprising, but it's important. That's the Jones polynomial of that L plus there. L naught we saw was the unknot, so that's got Jones polynomial 1. So now I have 2 of the 3 pieces in one of those, that skein relation. So there's the skein relation up at the top there. That's the relation, that was axiom 2 a couple of slides ago. You've got the 3 polynomials related, right, that equation 1. I know what L plus is, the polynomial of L plus, because we just worked that out. That was this. I know what L naught is. It's the unknot, and so its Jones polynomial is the number 1, so I haven't even bothered to write it there. So in equation 2 here, the only thing I've got that I don't know now is the Jones polynomial of L minus. So I do some algebra, and I get this. I don't expect you to check through the algebra, and in fact, when I check through it, I make a mistake every time, and I have to keep going until I get the same answer 2 or 3 times in a row. So don't bother about the details, but I have checked this 3 or 4 times, and and this is the Jones polynomial of L minus. That's not the trefoil that we started with. We're doing two steps here. The trefoil that we started with was T minus, and L minus was T0. And that, in equation 5, that mess there is the Jones polynomial for T0, which was L minus. T plus was just the unknot, so that x to the minus 1 times the Jones polynomial of T plus is just x to the minus 1 times 1. And T minus is the thing we wanted. It's the thing we wanted. And so now again, do some algebra on this, and you get that the Jones polynomial of the trefoil is that. Actually, you might think, that's not really a polynomial. Polynomials are supposed to have positive powers of x, like x squared and x cubed. Okay, these things are fancy things. They're called Laurent polynomials. They're allowed negative powers of x as well. But they behave algebraically in just the same way as ordinary polynomials. Another weird thing is that actually in the Skane relation, which is that thing at the top, you'll notice that there are some fractional powers of x. There are some roots of x. And yet in the final answer here, you've got whole integer powers of x. Is that always going to happen? Well, it turns out it will happen always for a knot, and it'll always happen for a link with 3 components or a link with 5 components. Okay, so it's the odd number of components have integer powers. Another thing that will have struck you by now is, my God, we did all this work, and this is the simplest possible knot. Okay, this was the trefoil knot. This is the one at the very top left of my table of knots. It can't get any simpler than this. And it's true, actually. You do have to work quite hard for these Jones polynomials. Imagine trying to work out the Jones polynomial of some of these things. Well, it's been done. It takes patience, actually. I mean, the techniques are exactly what I've shown you. Right? There's nothing new. It just takes care and patience. In my case, I'm not sure I would have it. But so here are some of the answers. This is the Jones polynomial of the third 6-crossing knot. And lots of Jones polynomials have been calculated. Now, the thing is that these Jones polynomials, they have the property that if you've got two and you calculate them given a diagram. Okay, that's what we started with. We actually had a diagram, and then we did these crossing changes and worked out these equations and blah, blah, and we got a polynomial out. And what you can show is that if two diagrams have different polynomials, then they must represent different knots. Okay? So you think, but what if they've got the same polynomial? Does that mean they represent the same knot? And the answer is no. Okay? These polynomials are invariants if in the sense that if two diagrams have different Jones polynomials, then they are definitely different knots. But sometimes the Jones polynomial gets confused. It's like my vision. There are some things which I can't distinguish, right? So there are some pairs of knots which have the same Jones polynomial. And a famous pair, they have the same Jones polynomial. I claim that they're different knots. Of course, how do I know that? Okay. Well, I have to use there are other invariants, not just the Jones polynomial. There are other mathematical invariants. Those of you who know about group theory, there's a thing called the knot group, which for the specialists is the fundamental group of the complement of the knot. And these two things have different knot groups. And so they're very definitely different knots. But if you calculate their Jones polynomials, you get the same polynomial. So Jones hasn't got perfect vision. There's a rather special relationship between these two knots. So you can see that there's a bit of it here that's been flipped over. And that's a very special operation in knot theory called mutation. And that's one of the things that in my own work I've been particularly interested in. Okay, now another big open question that I wanted to leave you with is to do with this problem of what Jones can distinguish and what it can't, what the Jones polynomial can distinguish and what it can't distinguish. And a very simple question is this: is it possible to find a knot which has Jones polynomial 1? Okay? We know that the unknot has Jones polynomial 1 because we rigged it that way. That was our first axiom. Is there, somewhere out there in the knotty universe, another knot whose Jones polynomial is also 1? And amazingly, in its full generality, that's still an open question. At least it was when I last checked. I've been away for a little while, but not that long. So again, if any of you find such a knot, publish it quick. Now, what I'm going to do is finish with a comment on some books. Absolutely my favorite knot book, in case any of you want to look into this subject further, is a book by Colin Adams called The Knot Book. And it's available from the American Mathematical Society. It's a paperback. It's an absolutely beautiful book, which I cannot recommend highly enough. He shows you all of these research questions and leads you through these wonderful open questions and all of this discussion in a way that I will never be able to do, however hard. He's really good. The second book I couldn't possibly recommend to you, but it's a book that I wrote with David Jordan some years ago, and it's a very, very gentle, well, as it says, it's an aperitif to the subject of topology, which is what knot theory is a very, very good test for. Now, and I should say that if anybody'd like to buy a copy, I don't have any on me, but I can take names and addresses and send them to you. With that disgraceful commercial, I'll end. Thank you very much indeed.
Two questions. The first one is, what does the X stand for? Because I missed that. I'm not quite sure in
the
Jones polynomial.
Okay, so let me answer them one at a time. So your first question, what does the X stand for? And I didn't tell you, because it doesn't stand for anything. Okay? It's just a marker. I mean, the X by itself really doesn't have any intrinsic meaning. The polynomial has a structure which is given to it by the relationship between various powers of X and their coefficients. Okay? What X is, it doesn't have any intrinsic, it just carries its power. So really, you could think of those polynomials as, I mean, you could represent them as a matrix, actually, with powers and coefficients. That's all the polynomial's doing for you. It's encoding the information between the powers and the coefficients. It does it in the correct way so that when you do that skein relation calculation, the algebra works out. So it doesn't mean anything.
Okay. Second one, 15 years ago, I started looking at knot theory for an application I was doing in physics. Can you tell me what the main application is these days for knot theory in the real world?
The real world? I thought I was in the real world. I don't know of any. I mean, it has very curious history because it was started about just over 100 years ago by physicists who were, this was before quantum theory, and they were trying to understand the structure of the periodic table of the elements. And there was a suggestion, a very creative one, that the elements were somehow knotted things. And if you could understand the world of knots, then maybe that's what the elements were. And so it was some physicists who first drew up tables of knots. Then along came quantum physics, and that all got chucked away. And then later on it was picked up by mathematicians, and it's now, as I say, a very important testing ground for ideas in topology. I don't know whether it has any. I mean, the thing about mathematics is that you can do a piece of mathematics with absolutely no visible application whatsoever, and then maybe 100 years or 1,000 years later, something really important to us depends upon that piece of mathematics. And it could easily be that knot theory is a case in point.
My work was 15 years ago, and I was looking at solar flares, and they're very twisted.
Oh, actually, that's interesting. So, yes, there are these twistings. The magnetic field lines are so strong, aren't they? They force the particles to.
Now, there's energy in twisting.
Yeah, I mean, so another interesting piece of history here is that the very first mathematician to write down anything remotely approaching a knot was Gauss. So some of the orbits of asteroids actually interlace with each other. And he knew that, and he was trying to understand how to describe those interlacing orbits, not from the way we would do it now dynamically, but just actually from a topological point of view, but he didn't have topology or group theory or anything at his fingertips at that stage. Okay. Yeah, so but I can't tell you what your particular speciality has, what's happened to it in the last 15 years, I'm afraid.
Okay. Does the degree of the polynomial tell you anything about the knot?
Good question. Because these polynomials go both ways, right, let me show you one. So if you look at this one here, just counting that, which is what you would normally call the degree of the polynomial, doesn't tell you what you need to know, because you also need to know how far it goes in that direction. So actually taking the width between the 3 and the -3, which is, I can't remember what the word for it in the technical lit, the span. Anyway, so it's the sort of the width of the degrees. That does tell you something about the knot. I can't remember what.
So you told us that the different knots could have the same Jones polynomial.
Yeah.
And purely empirically, how good a discriminator is it as you move up the number of crossings?
Yeah, okay, so that's a good question. So it was, when it was first discovered in '85, it was a lot better than any of the preceding polynomials. There were some other polynomials that had already been discovered by Conway and Alexander. And Jones was much sharper, had better vision than those polynomials. And then after Jones, another, in fact, it was a very interesting example of how different groups of mathematicians working independently can be moving in the same direction. And several different groups of people independently discovered a two-variable polynomial, which is called the Homfly polynomial, of which Jones is a special case. And that's, of course, even sharper. So that's a sort of answer. I mean, yes, it was better than anything that had come before, but the Homfly is sharper still. The difficulty we have is that because it's defined in this recursive way, we don't know in advance what it's measuring, you see. Whereas the Alexander polynomial, which was written down in the 20s, I think, was built up out of pieces of algebraic topology. And so you knew in advance what sorts of things it would be able to detect and what it wouldn't. Whereas with these things, you don't know. And in fact, one of the key research challenges for us is to find a topological model for the Jones, not just a recursive definition for it, which is very useful, but actually to understand what it means topologically. In other words, to get a precise answer to your question.